My name is Christopher Jones, and today I want to walk you through a system simulation workflow using the 3D Experience platform. In this example, we want to design a thrust reverser for an aerospace turbine that you might find on a commercial jet. On this slide, we see an overview of the different steps that we're going to undertake. We start at the center or at the start of the spiral at point 1. We define the system requirements, then we move on to defining the functional architecture, the logical architecture, before actually designing our physical product. Having built the physical product, we can then use integrated features of the 3D Experience platform to automatically generate a systems model. Once we've done that, we can mesh the geometry, run CFD simulations on our system in order to generate a surrogate model. Once we've generated a surrogate model, we can implement this within our systems model and run complete system simulation using the surrogate model, which is significantly more efficient and takes significantly less time than running a full co-simulation between the systems model and the CFD model. Once we've built our complete systems model, we can then optimize the system parameters using Process Composer to then analyze the results in Results Analytics. With that, let's get started. We have a whole host of requirements defined and organized in different chapters. We have power requirements, thermal requirements, and geometric requirements. Different requirements might have test cases associated with them that take into consideration different load cases for our system. We then use these requirements within our 3D Experience platform, where we can navigate them within the rich client. And once we've defined the requirements, we go on to define a functional architecture. A functional architecture defines the actual functional workings of our system, what functions our system is supposed to perform, and how the different functions are connected and what information passes between them. For each function, we can see what requirements are implemented by this function, and we can see what logical components implement this function at a later stage. For example, for the power system, we can dig into each function, see system functions for the subfunctions and how they work together. Once we've defined our functional architecture, we move on to defining a logical architecture. The logical architecture is much more related to the actual implementation of our system, focusing less on the functions but more on the how it's actually going to be implemented. Again, we can see for different components in our system what functions and requirements are implemented by each block and how they're connected. From that, we can then also build our physical model using CATIA. We have a model of an engine turbine which has a thrust reverser attached to it. The thrust reverser is nothing but a door in this case that can open and close, and we can see if it's opened, the turbine is, for all intents and purposes, closed, and wind would have to escape out through the door. Clearly, if we open the thrust reverser door, loads onto the door will be significant. We have 6 points on the surface of the door for which we want to determine the load on our system. Now that the physical model has been built and defined, we could define the mesh of our system in order to then run a detailed CFD analysis using our Simular tools. Having used the CFD tool to calculate the loads on the 6 points of our door, depending on the opening of our door, we can generate a surrogate model. A surrogate model in this case is nothing but a table-based model which, depending on the displacement or opening of the door, applies a different load onto the 6 different points. This surrogate model can then be used within the system simulation environment to describe the resulting behavior from the CFD simulation. Now, as our physical model has been built, we can go into our system simulation model, where we see the kinematics model has been automatically generated from the CATIA mechanism. We can see all the different components of our system, They all have the mass, center of gravity, inertia, etc. associated with them. We don't have to calculate these or transfer these manually. Also, we can see the degrees of freedom and the joints connecting all these different components. On the top, we see the 6 points on the doors on which we want to apply the loads. So if we go back to our systems model, we have our surrogate model associated with it for different load cases, which, depending on the position of our door, applies a load onto the 6 points. The input of our system is a force, and we're just applying a ramped force into our system, which is supposed to then open the door, and depending on the displacement of the door, load forces are going to be applied from our surrogate model. So let's run the simulation, and we can look at the 1D simulation results. So for example, let's look at the position of our door. We can plot the 1D simulation results and see the resulting animation in the 3D view. We can see the length of the force arrows changes depending on the displacement of our door. What we see here is A, that the door clearly oscillates and the door doesn't open completely. Now, in order to get rid of the oscillation, we might need to add a damper system to our model. So let's go ahead and do that. And we're just going to add a spring damper system from the Modelica standard library into our systems model. Connect it up to our prismatic joint and give it some meaningful values for both the spring and the dampening coefficient. With that, we can go back to our overall systems model and rerun the simulation. Hopefully we will now see that the oscillation has been dampened out through the introduced spring damper system. So again, let's plot the simulation results and look at the resulting animation. And what we can see is that the door opens and no longer oscillates in the wind. So we've been able to get rid of the oscillation, however we can also tell that the door doesn't open completely. So the applied force to open the door is clearly not high enough to counteract the load forces which are being applied to the 6 points. Now, rather than trying to manually find an optimum force that we can apply which is high enough to actually open the door in its entirety, but not too high in order to waste energy, we're now going to run parameter optimization using Process Composer. To that end, we need quantities that we want to optimize. And in this case, we want to optimize the integrated signal of the position, so the area underneath this curve, in order to maximize the displacement. And we want to look at the minimum of the derivative of our input, so the flank shouldn't be too steep. With that as our output signal, let's look at the optimization process that we might use. We are using the 3DX utility, which is calling the systems model we saw earlier. We have 2 inputs for our system model, the ramp height and the ramp duration of our excitation. And as outputs, we're interested in the maximum values for the integrator and the derivative that we saw earlier. Now, wrapped around this individual component, we've added an optimization block. And this optimization block is going to run 100 iterations and change our 2 input variables between given lower and upper bounds, and is going to try to minimize the derivative and maximize the integrator value. Now, the optimization takes some time, so luckily I've run an optimization earlier using the same setup. We can now look in detail at the simulation result. The simulation results are visualized using Results Analytics in the browser, and we can see the different parameters that we have, both the input variables and the output values. We can explore the entire design space that has been optimized. We can look at all 100 simulation runs, compare them with one another, and there are lots of different visualization methods that we can use to help us make sense of the optimization results. We can look at scatter plots, which help us identify trends in the simulation results, and there are lots of other visualization capabilities available depending on what's of interest to you. Once we've evaluated all our simulation runs, we might choose to look at a handful of simulation results in greater detail. So we would add them to the basket in order to then compare them. And we can see in this spiderweb diagram something that's very typical. We have two quantities that we're trying to optimize. We want to minimize the derivative and maximize the integrator value, and it's not always possible to achieve an optimum for both, so that it's necessarily to do a trade-off. What is more important to me? It's also possible to change the weighting between our optimization outputs. We might determine that the integrator output is more important to us than having a gradual slope. So we can change the weight, which would change the order of our simulation results. Based on that, we can then make a selection and recommend these to our colleagues. We can enrich our selection with comments detailing why we think this is the solution that should be implemented, and then submit it. All our colleagues working on the same data see our decision, they can see why we chose to select this optimization output, and they can then run their own simulations, argue their own case, and collaboratively we can reach a conclusion. So we've now chosen this optimization result as our optimum using the two parameters shown here. So the ramp duration has been increased to 8 seconds and the ramp height has been increased to 12,000. So let's take these values and go back to our systems model and rerun the simulation using these new values. 12,000 for the ramp height and 8 seconds for the ramp duration. Rerunning the simulation and looking at the simulation results, we should see that the door now opens completely. We no longer have this overshoot at the top of the ramp, and overall a much more gradual slope. So let's look at the simulation results one last time. We can see the door gradually opens, then ebbs off, opens all the way, and comes to a standstill. So this is the sort of behavior that we're looking for. And with this information, we could now go on to the next step and design a more realistic opening system, for example, using a hydraulic actuation system. With that, thank you very much for your attention. Have a great day.